from this lecture onwards we will look at several for several lectures we will focus on parameter estimation. We will first start with biochemical systems theory and start seeing how we pose parameter estimation as a nice optimization problem. Okay. So, welcome back. Today we will look a little more at dynamic modeling and particularly focus on a very important aspect of dynamic modeling, which is parameter estimation. Typically you will have a good data set, hopefully a data set of good quality, quantity, reproducibility and so on, which you need to employ to identify parameters for your dynamical system of interest. So, how do you do that is something we will try to discuss and understand in the coming lectures. So, before we go there, there is also this classic field of study called biochemical systems theory, which essentially tries to cast all the different kinds of models we studied yesterday. We briefly talked about Michaelis-Menten models, mass action models of course, and your Hill kinetics and so on. It tries to cast all of these models with inhibition, without inhibition, with competitive inhibition and so on. It tries to cast all of these into sort of differential equations which involve power laws. You can see the power law here, right. So, dxi by dt is some product of xk raised to some power. What are your xi's? They are your concentrations of different species, right, typically, right. Your mu ij are like your stoichiometric coefficients, you have rate constants and the kinetic orders, and the orders can be negative and so on for inhibition and things like that, right. And in reality you will not find that something is like purely a second order reaction, it will be like 1.8 order reaction and things like that. So, those are the kind of exponents that you will end up having in these systems, and these power laws can also faithfully model the non-linearity of biological systems. They also give you usually saturating response, they do not give you like unbounded responses and things like that, they end up giving saturation responses and so on. So, given a system of this sort, a typical challenge is you hopefully have generated some data or some biologist has come to you with some data on a particular system, right. So, how do you then model this system, or how do you in fact how do you model this system? The first step in modeling is you understand the system and write out the equations, but the moment you write out the equations you still do not know the value of any of the parameters. Until you know the value of the parameters you can't make any worthwhile predictions. K is for every species, right, all species x1, x2, x3 over all the possible species, right. Many of them may have 0 exponents and things like that, so it does not depend on them, but so let us look at the data analysis part. So, I think most of you must have carried out a Michaelis-Menten kind of experiment in the lab. So, what would you normally get from that experiment? So, what is the data that you normally get from a Michaelis-Menten experiment, and how do you do the delta S by delta T? How do you know the exact T? T keeps ticking, no? How do you stop T? You like put it in ice, no? Yes, remember? You basically literally stop the reaction by putting it in ice, and then you make the measurement, and then you compute some delta S by delta T or something. This will approximately be equal to your V at a particular time, right. So, you will essentially end up computing something like, is this right? So, you will have T and V, and of course S. V is the rate of the reaction. In fact, you may not use T as well, right, in the experiments. You basically just compute the initial rate. So, you compute V and S and you fit it. How do you fit it? So, there are 3 different ways to do it. There is the Lineweaver-Burke plot, there is the Edey-Hofstee plot and the Haynes-Wolff plot. What are the advantages and disadvantages of each of these? I am not going to go into it, you would have studied it in a classic biochemistry course. But the one thing to note from the point of view of this course is these transformations are problematic, right, because what happens when you transform something, you are transforming something, right, you are taking V, taking reciprocal, you are taking S, you are taking reciprocal. V cannot be 0, so you will have some behaviors close to that 0, that is one thing. Your errors also get transformed. Usually it is fair to assume that your errors are normally distributed. If you have or you can assume different kinds of noise, but basically
Central limit theorem.
central limit theorem, right? But what happens in these cases, this error, the errors now get transformed, so all those assumptions no longer hold, which means that you have the math that you are using is going to be problematic. Okay. So one thing that I would normally suggest is it's time to forget these plots. No, I think classic biochemists would be will cringe at that, but basically how do you estimate the parameters now? Okay, why did we use these linearized plots?
Straight line is easy to draw. There's any deviation.
Why is a straight line easy to plot? Right? So it's just so that you can plot these points on a graph paper and then see what is the correct slope that will. If you were to do it systematically, you would still have to have used a computer, right? And if you are anyway going to use a computer, might as well do non-linear fitting. Why do you want to do linear fitting? Linear fitting is good for graph papers, right? So these plots are still useful in terms of maybe getting a decent guess for V and S, but a two dimensional problem is not at all hard, so you do not even need a decent initial guess for V and S. So these have been used heavily in the past because of simplicity, but the main problem is that transformation of data changes noise characteristics, but we can still use it now perhaps to feed an initial guess to a more complex estimation algorithm. So this basically goes back to curve fitting, right? So let us say you have a few data points here. You now want to fit a good curve through this. You may want to fit a curve that looks like this. This is essentially or parameter estimation. How do you do this? Okay. This is a very interesting problem, and this is in fact the most of course one would say that the most important problem in modeling is trying to build the model in the first place, but that process itself is incomplete before estimating the parameters, right. I could come up with an arbitrary model if you can never find a parameter set that can connect this model to my real system. By the real system I mean the data that the real system threw up. If you can never connect the two, then you do not have a model in the first place. The model is not tenable for this purpose. So parameter estimation, you can imagine, is an optimization problem. What is it that you want to optimize? You want to basically improve the fit to the data, right. So there are various ways to pose it, right. A Bayesian person would say that can you maximize the probability of observing the data given a parameter set. So you want to find the parameter set that maximizes the probability of observing the given data set. That translates to a maximum likelihood and so on. But what is it that you really want to optimize here? So let us look at this example, this very example. What is a good curve? This can become a very interesting question, right, and this is where this is still an open question. It might sound sort of simple and trivial, but what really is a good curve? So let us say I agree with trend. What does it mean by trend? Or rather than trend, can we now look at key characteristics of the curve? What could be the key characteristics of a curve? You may have a delay, meaning like this. So you may be interested in capturing this delay in your model. You may have a peak. are you able to capture this? Very commonly you may have a steady state. Can you capture the steady state? You may have a delay in the response, right? There is some, so let us say you administered a drug at time t, time 0, right? You could have different responses for this. It could start like this, it could go like this, it could go like this. Which of these is, so if this could be from your model, right, and your real data let us say looks somewhat like okay, let us just assume which of these 3 is good, because if you were to compute some least squares or something like that, you may not be able to truly say which of these is good. You may want to subjectively attach much more importance to one of the features. It could be the steady state, it could be the peak, it could be the delay, right. What is more important? This is very subjective, right. This means that you need a very intelligent way to estimate parameters, and this is something people normally do not do. So, I will tell you what people normally do. So, in this video we had a brief overview of biochemical systems theory, and we also studied what are all the various ways one can specify an optimization problem. Typically a good least square fit is a classic strategy. In the next video we will continue to look at what are all the challenges in setting up a good optimization problem which helps us get good parameter estimates.